Hello everyone, welcome back to week 7 of deep learning. So, like the previous week, this week again we'll be going through the concepts which was covered in the week 7, and then we'll be solving some problems which was asked in the last year quiz, so that it will be easier for you to go through the assignment problem on yourself. And if you have any doubt, feel free to ask. So I hope let's get started. Okay. So this week what was covered basically it was mainly related to the performance of the model that the deep learning networks we are having. So the deep learning model, what we want is basically that it should perform good on the unseen data sets. But how to quantize that? How do we know that our model will be performing good in the real world task? Because otherwise, if it's not performing good, it's useless. So that's the purpose. We want to measure that how far it is apart from the real decision which we want. Okay. So to capture all these things, there are certain things which are used so that our model should perform well on the unseen data set. So the first thing we'll be looking it will be Paras, variance, trade-off. Okay. Then again, something related to test error and train error. That is what is train error and test error. Okay. Then something called model complexity. That how do we know that, for example, the deep learning, we can take many number of neurons, large number of hidden neurons. Okay. So our model can be of 2 layers as well, 100 layers as well. So we want to see that which model to pick basically. So that is where this model complexity will be coming into the picture. Okay. Now we know that, for example, we are having a training and a testing data set, and it's performing very good on the training. But we want to perform equally good in the testing as well. So think it in this way. The Tesla car is there. Okay, so it's automatic basically. So was performing very good in the lab testing and all. But when you put it on in Indian notes basically, then it won't perform good because it haven't seen that kind of a data. It can't make a proper decision whether to take right, left, what is speed, angular speed, and all. So, but we want it to perform good as well. Okay. So that's where we'll be seeing some of the concepts to avoid overfitting, which will include L2 regularization, then data augmentation, weight sharing, then adding noise, to input or output. Okay. Then a restopping. So by name, a lot of things are very much clear. Like adding noise, we are adding the noise. A restopping that we will be stopping a model very means after 100 epochs. We won't be training for the 1,000 epochs. So that's what we meant basically. But I will be just giving a guess at what actually it meant intuitively. Okay. So I hope you have went through the lecture material so that it will be easier for you to grasp the concept which I am teaching today. Okay. And finally, drop out and assembling of methods. Okay. This Sincerely telling, the research in the ML community mainly revolves around this whole stuff actually. So a lot of people talk about variance bias trade-off, how to handle it, okay? And model complexity, how to make a simple models so that it generalizes well, okay? Coming up with a kind of a new kind of a loss functions, okay? That loss should be better than the previous loss, okay? And weight sharing. So this is kind of an inductive bias. Okay, inductive in the sense, for example, you have a time series database, that time series data set, where you take a last 10 time step, try to predict 11th one. So we do auto-regressively. So RNNs and all, you might have heard of transformer and all, okay? So that's where we want to design an architecture which is suitable for certain kind of a data set. Not all the data sets can be applied to all the kind of a model which we have seen. Okay. Regression you can't apply basically on a time series data. You need to have a kind of a model which can capture the latent representation that how it is changing. Okay. So let's get started. So firstly, we'll be talking about bias variance trade-off. Okay. That what is bias and variance and trade-off. So as I mentioned that the real world data set is very complex. Okay. And the neural network, the chat GPT, if you see basically, so many of you might be using the chat GPT and all, okay. It is consisting of billions of parameters, 7 billion, 70 billions, like that. Okay. And that's a huge number of weights. Okay. But still then it is performing good enough on all the tasks. It is better than 80% of the humans. Okay. Still 20% is remaining, but yeah, its performance is equivalent to around 80% average human beings. Okay. So just how do people came up with such such models basically that it's performing equally good? For example, you want a very short task, if you give it, it's performing equally good there. So how they did it basically? The question is that. So the answers lies basically that how they designed their training of the model. Okay. So for example, I have an underlying function basically from where I am having a data. Okay. And the underlying function suppose is f of x. Okay. Which is basically sin x. Sin x looks something like this. Okay. Now I have been given certain data point. Suppose like this. Okay. And I want to explain this data. I want to fit a curve. Okay. Machine learning is all about fitting a function. That's it. Nothing else you are doing here. Okay. So you are given a data set. It can be of arbitrary dimensions. Okay. And the purpose is basically about we need to fit a curve so that it is as much closer as to the unknown function which we don't know basically. Because the unknown function, if we know, our work is very much easier. Okay. But the thing is, we want to quantify that thing, that how much closer we are to the true function which we don't know. So that's why we are talking about bias variance trade-offs, okay, overfitting, underfitting, and all this thing. And how do we measure it? To measure this all quantities, we just have a training data sets and a testing. So if we have fitted a good function on the training data set, and which is much more closer to the true function, okay, then it should perform equally good on the testing data set as well. That is what we hypothesize. Okay. So basically what we want is that if we have a data set which is performing good enough on the training, so that we expect it to be the true unknown function. It has approximated it quite well. Okay. And whenever we pass a testing data set, it should perform equally good on that. Okay. I hope this point is clear. Okay. So as this function is given, okay, and underlying function was the sin x, which I don't know. I don't have access to it. Okay. But I have access to the sample. Okay. So my data set looks something like this. And I want to know that which is the true function from where we can fit a curve which explains this thing. And suppose we have a testing data set, suppose as well. Okay. So the purpose is that, as I mentioned, we need to fit the curve so that it performs good enough on the training data set as well as on the testing data set. So that's the point. Because if it's performing good enough on training and not on testing, that's useless. If it's performing well, bad on training, it might not perform good. It won't be performing good at testing the testing. That's what you can think. Okay. So that really happens that a model is performing very poor on the training data set and suddenly it's performing too good on the testing. So that kind of a case very rarely happen in machine learning. So the only thing which happens is that you want to model to perform equally good basically. Okay. So I can fit a lot of functions because as the underlying function, I don't know. I can fit something like a straight line. Okay. I can fit something like a parabola. Okay. I can fit something like higher order degree terms, something like this. So a lot of functions can be fitted on it. Okay. So in the end, our purpose is to minimize the loss. During training, what we minimize the loss, which is prediction minus root square. RMSC loss I'm taking, root mean square. Okay. And it's with respect to all the data points from I1 to N. Okay. And what we want is that it should perform good on testing data as well. Okay. So in the testing data, the loss should be as minimum as possible. So in the end, it should perform good. Okay. And we don't have access to the testing data because real world data. So for example, a chat GPT, okay, they have trained it on tons of data, but still it okay. And for seeing that how it performs in the real world, they have deployed it. So sometime it might some hallucination task comes. Okay, you want to give a matrix multiplication and all, it won't perform good at all. Okay, because it might have not seen such a type of a data at all during the training. So a lot of possible reasons are there actually for this thing. Okay, so we want to talk about that if my model is performed. So I have a two kind of error: the training error and the testing error. Okay. And basically, I want both of them to be as minimum as possible. That's what an ideal model should do. Okay. But it doesn't happen really actually. Okay. Sometimes it performs good on training, bad on testing. Okay. So a lot of combinations are there actually. Bad on both this thing. Okay. So for example, here if you are fitting a straight line to the sin x curve, okay, this is straight line, something. Okay. So you might be saying there is a lot of explanation. It's not explaining well for both the training as well as testing. Okay. It is good because it has seen a less data, but as we don't know that what's the underlying data, the underlying function from where we have sampled this points. Okay. So it become a quite tedious task here. Okay. So we will be measuring this that if we are given certain training, certain tests also, okay, how do we quantify that our model is how good it is actually? Okay. So suppose if we be taking a 2 months, there was two example which was considered during the week. Okay. So the two example which was taken was simply one is straight line, Wx plus b. And the second was something like W1x plus W2x square something plus W25x to the power 25 plus b. These two models. So this is my model one, this is my model two. Okay. So I'm trying to run the weights for both the models. Okay. And I want to know that out of these two models, which one is the best? So you might have seen a leaderboard of ChatGPT, Mr. is there, Ramba is there, Gemini is there, Google. Okay. So they have been a leaderboard that this model performed this much on this particular task. Okay. So this is how we quantify the performance of different models. Okay. Okay. So, but one thing, if you see this first model is very simple model, and the second one is a quite complex model. 25 degree we are going with. And the number of parameters, the more complex model you take, the number of parameter increases exponentially. See, the task of in the machine learning, if you're making a model, the model should be as simple as possible and it should generalize well. That's it. How to come up with a model which is having a less parameter, less complex, and generalizes better. That is a kind of a task. Okay. So if you see both of this model, if I had this data set, my state and might perform is something like this is what it learned basically. And if you see this order 25, it has simple model. It was underfitting. Underfitting means that it is not explaining the training as well. So we use two: underfitting and overfitting. So underfitting means it's not fitting the curve properly at all. So that's what we call it, is underfitting. Overfitting means it has some ziggly wiggly kind of a shape and it is overfitted. It means the error is zero basically. Okay. But also it's not performing good in the testing data. Okay. So, but we do want to quantify that which one of them is the best. Okay. If you ask which one of the I need to pick, I will mostly go with the first time kind of a model because this is a very simple model. Okay. It might be very means what I say, not explaining the training data set well. Okay. But you should always just remember the golden rule in machine learning. The simpler the model, the that you should pick. If you are given two model, one is having both of the performance are comparable kind of, always pick the model which is much more simpler. Okay, because that's the thing we want. We don't want to have so many parameters and simple model is performance equal enough, then we don't need that many parameters actually. That's what it's meant. Both of them will be performing poor on the testing data. But how do we quantify this whole thing? So suppose we are given a certain means 100 points or something like that. So we just pick some sample some points from the training and sample means run different models. Okay, different models with the same kind. So for example, I will be running a 10 models for this kind. Okay, and 10 models using a simple model, the simple one. And then I will be taking an averaging of both of them. Averaging, and I will try to see the it means average that if my sample point is sampled, then what's the average function I'm getting it in both the cases. That is what we call it the expected means expected function, and the variance, that what's the variance of the function. Okay. So the thing is, the simple model, it is whatever you point you take and you perform k times, it will always remain the same around. Okay, it does not fluctuate around. So that's the thing. But the second thing is it is very kind of a high error. Okay, and it is underfitting basically. Okay, but on the same side, if you see the complex model, it is overfitting. But every time the shape it is fixing is different for the different kind of a sampling you are doing it. Okay. So how can we mathematically describe this phenomena basically that what we want? Okay. So that is where the concept of this bias and variance. So bias, you can think it of as the averaging. Okay. So if we take an expected value, okay, that we have fitted a different function, and if we take an expected value of that function, okay, so it will be just the bar. This is what we are interested in, and if we minus the two function f of x, this is what we call it as bias. And variance, if you see it, we call f cap of x. This is our model minus expected value of, yeah, expected value of f cap of x. Okay, this whole thing square, we call it as variance. So normally in the Gaussian distribution, if you might have seen that what is the Gaussian distribution, we have something like this is the distribution for the random variable x. And mean, we take it as mu, and this denotes the sigma. So what does the mu denotes? Mu kind of a averaging we takes, average, okay? And so basically it's something like this. I have been given two clusters basically. Okay, being give you the average of the clusters or different samples. And this variance kind of it denotes this radius, that how much far apart it is spread. Okay, so that is what the variance does. It tells you, for example, my data samples are kind of this much where means far apart from the mean basically. So basically what you want is your variance to be smaller, because if there's a large fluctuation, then it's kind of a hard to explain that phenomena basically. Okay. So this two definition, you might, it's common in whatever the random variable if you take. Okay. So basically a simple model. So in the simple model, there's kind of a bias. It wasn't changing means a lot. Means the averaging effect was not changing, but the expected value from the deviation from the function was high, because f of x, the underlying function, was sin x. And here we modeled it as just a linear function x. Okay. So the bias for the simple model was high because it was not explaining the expected value, was much more far apart. Whereas this complex model we had, okay, the bias was low. It was explaining well the averaging. Okay. But the variance, if you see the deviation in the samples for the simple model, it was kind of not rotating a lot. But in the other case, in the complex model, the variance was high. Okay. So simple model comes with the high bias, low variance. Complex model comes with basically kind of a low bias, but high variance. Okay. Basically what we want is low bias and low variance. Okay. So we need low bias and low variance. That is what we need basically. Okay. So basically there is a derivation which was did in this week, I guess. Okay. The expected value of y minus f cap of x. Okay. Whole square. You can write it as Paras square plus variance plus some constant which is irreducible. So this y is the original data, means regression. For the regression, it was the value y of. So I have taken basically for regression basically so that it's easier to interpret. So this is the RMSC loss we are taking it. Okay. And we can decompose it into a bias plus variance plus some constant. Okay. And so our total error, we were minimizing this. Okay. So this minimizing, we have a two control, bias and variance. Okay. By minimizing this, we can't ensure that whether it will be having a high bias or high variance. Means which one is a higher? We don't have a control over there. So basically, but we want to control the bias and variance as well. Okay, because our loss we can decompose it. And basically, how do we do it? Basically, is you can add minus expected value of f of x and add it, and then expand it. You'll be getting this kind of a form. Okay. So for the derivation, refer to this weak correction. Okay. So basically the model, whenever you are minimizing the loss, okay, the loss is getting minimized, it's okay. But our loss is composed of bias and variance, two terms. And with respect to the loss, we don't have a control over bias and variance. But we want to have a controls. What we want is both of them should be low as well. If one is low, other is high, that is not what we want basically. So you can think it of as if our expected loss is something 10. Okay. And bias will be 2 and 8, variance is 8. Suppose I'm doing this constant. 2 plus 8 is also 10. My bias kind 4 and this is 6. This is also 10. 5 and 5, this is also 10. My bias can be 8, this is 2. So something like this can be there. Okay. So, but what we want is ideally both and both bias and both variance kind of a, the proper estimate should be this should not be a very higher bias or very higher variance. This should be approximately equal. But as of now, with the loss function with which we are running our model, we don't have a control over bias and variance. So the techniques you saw, okay, the stop out, ensembling, okay, and regularization of data augmentation, adding noise, this all stuff is kind of with controls. Control in the sense we want to control the bias and variance of our model. So you add an extra term to the loss so that it incorporates this bias and variance and try to make sure that if my bias is increasing, the variance should also get increased. So loss will be overall increasing. So if my bias is decreasing, the variance should also decrease. So something like this is what we want. Okay. So there is one very much common bias variance trade-off curve. Okay. So whenever you model complexity in the sense, so one exercise which you can do is that go and pick any linear regression data set, okay, and with the polynomial try to fit from a linear to the 100-degree, okay, and so that will represent the model complexity. As the number of parameter increases, the model complexity increases, and plot the loss, okay. So you might be seeing the training error. The more and more complex model you take, the training error always goes to around 0. Okay, it might mean 0 basically because it will just fit every curve properly as we saw in the Sinex. We were taking a 25th ordered. Okay, but the thing is, this is about training. Training curve will follow this thing. Okay, but the testing loss will also decrease, but with time it will increase. Okay, so this always happens actually. Okay, so that's why I'm suggesting you go and pick any data set, try to do the linear regression using a scikit-learn, okay, and see this phenomenon. It will happen everywhere. Okay, as you increase the model complexity, okay, our training error reduces, but the testing reduces, then it increases. But what we want, our purpose is to testing error should be as much as minimum. Basically, that's the purpose. So basically, this is the sweet spot. So the whole thing about this adding noise, editor regularization is just finding this sweet spot where our testing error is as minimum as possible. Okay. So that's why we do with this all kind of stuff. So if our model is very means complexity is very low, so that is where the simple model, so it will be high bias. This region is high bias, this region is low bias. Okay, this region will be high, low variance, and this here will be high variance. Okay, so this is what happens basically. So our basic thing is just to finding a sweet spot. So that is where it will be coming. So perfect trade-off between bias and variance trade-off. Okay, you can't have a model where you just say that my see it's something like my error is composed of two things. In this case, bias and variance. Okay, so if you try to have more control over the bias, you lose the control over the variance. If you try to have more control over the variance, you lose over the bias. The same analogy, if you see, whenever you are driving a car, you have your legs on the brakes as well. Okay, so if you are applying just continuously the brake, the car won't run properly. But if you just lose the control over the brake and just driving in, then it will be very high speed. But we don't want that because on the car, whenever you are driving a car, you should have a control over the speed and all. Okay. So that is where you put your legs on the brakes and hands on the this for the controlling the speed basically. Okay. So you try to balance basically. If you are increasing the speed, you try to apply the brake. Okay. When you are decreasing a this means if you applied a lot of brake, basically the speed is very slow, then you try to increase the speed. So that is kind of a trade-off which is happening. So that is what we want in the model as well. Okay. So I guess I have given you the enough intuition that what actually is happening, what we want. Okay. So there's some mathematical thing that was did in the week lecture was basic expected value of the prediction minus the two. Okay, we can decompose it to getting some error term. Okay, so that derivation I'm not going to do basically. Okay, so if anyone wants, basically the thing was if we have this thing expected value of y minus f of x, if you want to decrease this thing, okay, then this expectation is over the distribution of x and y, but we don't have all the samples. So how can we estimate this? So there is a thing which is called we will be doing empirical risk minimization ERM. We have access to sample. We will be taking an averaging over all this loss. Okay, over I from 1 to n. And if you want to know why this is applicable, so the one thing is law of large numbers, large numbers of samples. Okay. So if we have a more sample, then we can estimate this empirical means this estimation with the empirical risk minimization with the samples. Okay. So this is the common technique, which is, for example, you might have known about the center limit theorem. So the center limit theorem, what it states that if we have a certain distribution, okay, if we get more and more samples out of that distribution, and if you take summation over all the random variable and divide by n, this tends to mean of the distribution. Okay. So if it doesn't know, I'll be just suggesting just go through the center limit theorem and all, because you'll be getting that why this expected value, we can write it in this kind of a Monte Carlo approximation. So you can just search on the net Monte Carlo approximation of expectation and like that. Okay. Okay, so that was about the bias variance trade-off. You can learn about covariance matrix if you're not sure that what's the covariance. It's kind of an easy thing, but just brush up the same simple probability basically. Okay. Now the thing was now the next thing is in the week lectures basically they showed one thing was to uh, they decomposed it as empirical risk minimization. Okay, empirical risk minimization. Risk I'm calling the loss basically. That's the standard term which is used in if more mathematical kind of a machine learning. Okay, there's some constant is model complexity. This constant we don't have a control. It's always a constant. The two errors. Okay, this thing we can calculate with the samples as what I showed. But this thing, can we have certain things in our loss which can control the complexity of our model as well? Okay, so that it doesn't overfit basically. We want it to be, we don't want it to be underfit. We don't want to be overfit. If we start with a lot of parameters, basically, it will overfit. But can we put certain constraint on the loss so that it's in between underfit and overfit? And that is what we want, the trade-off between the underfit and overfit. Okay. So basically, we be adding certain kind of a regularization. So this model complexity. So the one thing which is done in the literature and empirically what people does is regularization, data augmentation, parameter sharing, what I mentioned, adding noise to the input, adding noise to the output, early stopping, assembling methods, stop out. So let's see one method, basically. Okay. We modify our loss with respect to weights W, the original loss in the regression, something, regression or the classification, basically. And we add this term. So this is the L2 norm. Basically, it is W transpose W, basically. Okay. So what this loss is doing is basically we are saying that we want to minimize the loss what we are having. This alpha is the hyperparameter which you need to tune it up. Okay. So it is on our control what we want the alpha to be. And see, as I mentioned, in the trade-off, we always have two terms and we need to balance. So this alpha balance that whether you want it to be more means you penalize the model more to be having a higher weights when it does overfitting. So how much you want to do. So this alpha provides a kind of a control. So this norm of W basically that is W transpose W. What it is saying is that we don't want our weights to be very large basically. Okay, we want our weights to be small basically as much as possible. Okay, so you can think it of as suppose the curvature of the loss curvature that is the 2D contour or something like this, which is very much along one direction. If you see, it is very skewed. Along another direction, it is very kind of a steep. This norm ball, if you draw the norm ball of this W basically, this is the norm ball in the normal circle. because L to norm, you can think it of as a circle, because along a circle, we have a distance, all of them as a equal. So that is what we call it as a norm ball. So the point where my both of this cuts and that this tangent and this tangent matches equally. So that is where this whole thing will be getting minimized. Are you getting my point? See, what I'm suggesting is that we have a two contour plots, one with this with respect to original loss, one with respect to this additional loss term which we are adding in. If you want to minimize both of them altogether, then the minima basically will be such a point where the tangent with respect to the loss first term should be equal to the tangent to the with respect to the second thing. And both of them should be add up in the opposite direction and they should nullify each other effect basically. So that is related to optimization. So if you're interested, just go through and just search about that, this Lagrangian multipliers and kind of stuff. Okay. And you can take a gradient of it. Taking a gradient is just alpha times W. So that doesn't change a lot basically. Okay. And you can think it of as you can do the Taylor approximation and all. So I'm not gonna cover that. If anyone is interested, basically they just refer to the slides. It has been properly mentioned that about the Hessian and the Taylor series extension and all. Okay. Now coming up to this data augmentation. Okay. So what is this data augmentation? So by the name, it's very much clear that we have a data. So suppose the model is there. Okay. The numbers 6 and 9. If you think it at that, if you see from the top, it looks, if you see 6 is there. If you see from the bottom, it looks like a 6. From the top, it looks like a 9. Okay. So what we want is that if we flip the number, okay, our model should, for example, initially it looks like a 6. So what will happen if I just rotate the number? Okay. I rotated it, it becomes something like this 9. Okay. There is 180-degree flipped I did. Okay. So what I want is that I wanted to classify this thing properly, basically. Okay, if I can have it do something like this, do something like this, do something like this. Okay. So different people write in a very curve and all something. Okay. And something like do something like this. Okay. This is all twos basically. But and because if you see that handwriting of the different people, they write different digits differently. And but what we want is that our model should perform equally good at all the type of handwriting. Because there's one thing common, the features. The one is that one will be always a straight line or something like this. Okay. So there is a feature that one basically just a straight line and nothing else. Something. So that is a feature of a one. Okay. 7 is there. 7 comes like this. If 8 is there, there's a 2 kind of a blob. Okay. So this is how the model should be. So it should not that if we rotated a number, it's giving a completely different random output. Okay. But that is what we do in the data's augmentation. So if we have a data set, okay, we can just rotate the data set, okay, and we can decrease the size of the data set. Because if we just diminish the size of the number remains the same. But model should understand that, no? Okay. So that is what we want basically. And the more the data we are having, the better the model will be running. Because it's like a child is born basically. Initial few years, he has been showed a lot of examples that this is apple. Apple is of red color. Okay, it is of this shape. Okay. So first time it is being showed, it just fixes in the mind. Next time, different shape of the apple, a small apple. Okay, very big apple, something like this. So with the time the child get acquainted with the lot of data set, and he learns or she learns basically how to classify this uh, any object basically. Okay. Now coming back to parameter sharing. So one thing is there, okay, in the traditional image processing, for example, we have certain image, okay, we have a flower, we have a man, suppose, and man is present here as well, okay. Both of them are the same basically, shape, size, everything is the same. So basically, what we want in the weight sharing is, by the name is that the weights of our model we want to share basically, okay. So okay. So the thing is, if my in the for example, this image is there, if I ask the model to classify whether it's a man or woman or whatever, okay, and if it gets shifted, the output should remain the same, basically. Did you get my point? I was present in a top corner, and if it gets shifted to the bottom something, okay, the model should predict the same because both of them are the human. But ideally, if you see, it doesn't. That's the issue. We need to have a model which can, irrespective of the position of the object, it should classify it as it is. That is what we expect to be. Okay. If I okay. So that is where we have a kernel. Okay. So this kernel, if we place it anywhere, top, bottom, the feature it gets out, it's remain the same. So that is what the weight sharing is all about. So I hope this you got this point. So if it is present on the top or the bottom, as we did the weight sharing of this model, it will always predict this as men irrespective where it is present. Top, bottom, right, left, okay. So this weight parameters are used in the CNNs, okay, filters, and previously, for example, in the traditional image processing, people were using making this kernels basically for the image processing, and that was a very tedious task. So when this ML, this CNN kind of LXNet in 2011 it came, okay, this thing changed completely because this kernels we made it learnable, okay, and previously human were making means try to learn basically that this was the edge detector, horizontal edge detector, vertical edge detector, and like that, okay. So this made the work easier, okay. Okay. So it is also used in the auto encoder, which we covered in the last week. So we had an encoder, we had a decoder. We can share the weight across both of them. The lesser the parameter we be having, the more the model generalizes. So that's the objective. Just having a lot of parameter doesn't mean your model is running something. Okay, you need to have a model which generalizes well equally enough. Okay. Now the third means the next type of this regularization we are having is adding noise. So we add noise, corrupt it x given x with certain probability. Okay. So where x is basically this we saw in the last week as well. So basically we add x bar is just x plus certain noise where noise is sampled from the Gaussian distribution of zero mean and unit variance. Okay. So the purpose we saw was basically that uh, the model should not mug up that, yeah, this is exactly the same thing. Okay. When we are when we are adding a noise and asking the model to denoise it, then the model is learning something basically. Okay. So it's kind of you can think it of as a puzzle. So during childhood, we give a puzzle, randomly shuffle, ask the person to play with it. So if he really have understood the concept, he will make the puzzle. So that's what we expect from the model as well. So that's the purpose of adding a noise. Just corrupt it, ask the model to fulfill it. Okay. And it can be shown that adding a noise to this input is equivalent to this I2 regularization count of the stuff. Okay. So for that also you can refer. And we can add a noise to the output as well. So suppose we have an input, okay, in the classification task. So for example, we might have a long label basically. Long label in the sense the cat was present, okay, means man was present, suppose. And I want to classify into man, cat, dog, something, 10 classes basically. So it belongs to certain class. The noise can be very much no, means the label initial given for the model to learn might be noisy, okay, but and we are doing minimizing it, so we are saying the model to learn incorrect stuff, okay. So it's like that if you tell means during the childhood, if I have showed you the apple and told you that it's an orange, then during your whole while you were growing it up, you will think it as an orange, but that is wrong, okay. So that is why we add a certain noise to the input as well, some epsilon, 1 minus epsilon, so that we can diminish the effect while the learning. Okay. So the care divergence we do and the soft, I mean, basically the hard label is getting converted into soft labels. Okay. Now coming back to the next thing, the early stopping. So as you know that the curve with the model comments, if we're training a model for the number of steps, okay, the training error reduces with more and more because it's overfitting with time basically, okay. And but your testing errors, you can monitor testing error, and it is something like this. Now the thing is, when you were at this point, you want the idea point is this basically, okay. So you just train the model and just keep watching at which point it was minimum, the testing error, not the training. Testing error, okay. You went ahead for certain number of steps, okay, and you know that my error is now increasing, the testing error, but the training error is decreasing. That gives you the indication that no, I need to stop my model, and the time step whenever the testing error was minimum, that is a perfect sweet spot. So that is what is called as the early stopping. Okay, you go k towards k step backward and just take that parameter. And thinking it is early stopping is also equivalent to regularization. Okay, so if anyone is interested, they can just go through basically it. Okay, now coming to ensembling of meta thing. Okay, so as for example, I have ensembling basically. So ensembling means taking a lot of different models, taking an average of all the models and giving that as the output. So for example, you and your friend is writing an exam, suppose two or both of them. You might have learned something, your friend might have learned something. Certain questions come, okay, then the uncertainty in the answering that question will be higher for both of them because you are so, suppose you tell this is my, your friend got the answer 3.6, you got something 3.9, okay. But you want to make sure that both of them, if you both of them combine your answer and give, then it should means that should be nearby basically, okay. So that is why if you take an average of both the answers and just give it, there's a fair chance that it should be correct. Okay, for example, in the case of regression, basically, okay. In the case of classification, if I have a 10 friends out there, seven, one of them are telling one, three of one of them are telling zero, I'll be taking a majority voting basically here and telling that the seven, whatever they told is the correct, I'll be going ahead with that. Okay. So that is what the ensembling is that. We train a lot of models, okay, and the output is just average of each model divided by number of models basically. Okay. You take an averaging of output of all the models. So each model is running something different. There will be a different kind of a perception means because every person have a different way of learning basically. Okay. So some people might have got the answer with some other method. You might have got the answer with a certain. That is what we call it as a features here. And you might have learned from the different book. Your friend might have learned from the different book, different method, everything. But overall, if you combine the answer, it should be the same. It doesn't matter that from where you are reading it, how you are featuring it. So averaging just taking a lot of model, taking an averaging. So that is what we call it as a bagging basically, and it works out. Okay. So I guess that is done now. Now the last thing we'll be looking at is the dropout. But for this averaging, this ensembling, okay, we need to have a lot of models. We need to train. So for suppose we need to train 100 models. Okay. So for example, in the case of neural network, okay, if you're training a big model and the thing is you need to take a 10,000 GPTs basically and taking an averaging of that GPT. It's not a problem because one GPT, the training it took was around 4 months. Okay, so that is not feasible at all in the neural network case. Okay, so how can we do that basically? How can we have an ensembling of prediction for the neural network? Okay, so in the neural network, basically, we have certain neurons is there, certain inputs will be coming into the coming. This is all the hidden layers basically, and the output will be giving it us. Okay, now each layer is connected basically. Okay, similarly here. Okay, now the thing is, what we are asking the question here is, with the just one model, can I give means 10,000 of models using the one model? That is, I can do the weight sharing across the model. The answer is yes, we can. Suppose we have a hidden layer, we have a 5 neurons up there. Okay, so suddenly if it drops, if I don't take this neuron, so the other weights which is getting passed here will be getting dropped. So what I want is that my model output should not change a lot. Okay. So like this, at each and every epoch, I'll be just dropping certain neurons at each hidden layer and try to update the parameter which was there. So it's kind of, you can think of that as different time we'll be having a different model basically. And the weight is getting shared across all this model. And that is what the dropout we call it as. With certain probability, with a binary random variable, you either take a neuron in the model or drop it. Okay. And that this is little bit computationally not that much heavy. Otherwise, you need to take 1,000 neural networks and all. Here with different probability, if you drop out different neurons, with that many combinations of neural network you can get. Okay. So that is the fairly means same weight is getting shared across all the network, sample a different network at each and every inference. And during inference time, we take a averaging of all this how many times each architecture was active basically and give the averaging of that. Okay. And backpropagation happens only with respect to that neuron which was active for that particular epoch. Okay? That is what was about this dropout. So I hope I have just refreshed the concept which was covered in the week 7. Now coming back to problems basically. So again, I will be solving the last year problems. Okay. So the first question, we generate the data using the following model. So the underlying function is given to us. Okay. So this is the Q function. Initially, we don't know, but here they have given. Okay. We are trying to fit two models. We have been, this is certain kind of a function. We have just sampled a point and that constitute of our training data basically. It means data basically. Okay. We are fitting two models basically. Okay. Using neural network. So model one is basically y is equal to w1 x plus w naught. That is a simple model. And another model two is x to the power 6, w to the power 5, x to the power 5 plus w 5, 4. It's the order 6 polynomial basically, okay? Okay, now two questions. See, the original is third order. The first model is trying to predict the means this third order with the first order, and the complex model is taking the sixth order. Now they have asked the multiple correct options. Model 1 has a higher bias than the model 2. The model 1, it was a simple linear, and the linear we know that it is a higher bias, so it is true. Model 2 has a higher variance than model 1. That is also true. We saw it because complex model is having a higher variance. In this case, it's the order of 6, but original is order of 3. Okay. So second option is also correct. Model 1 has a higher variance than model 2. No. Model 2 is a higher variance. And the lastly, the model 2 has a higher bias than model 1. No. So correct answer is model 1 is a higher bias than model 1. And model 2 has a higher variance than model 1. So this was the first question. Now coming back to question second. Okay. We fit a polynomial model of different degrees on a given data and observe the training and validation error. What degree polynomial should we choose? So here is the degree of the polynomial, and here is the loss. Okay. So basically, they have given 2, 3, 4, 5, 6. The training error something looks like something like this. This is the training curve. Model complexity, you can think it of as. And the testing is something like this. Okay. So what I told you, a testing error wherever it is minimum. If you have a different models, you want to choose which model to select, always choose the model where the testing error is minimum. In this case, validation basically, okay? So I will be choosing this model of degree 3. So answer is degree 3. Third question. Given two plots depicting two regularization techniques which we refer to the left plot of A and right plot of B, choose the correct options. Okay. So basically they have given two plots. Okay. This is the contour of basically it's the common contour for the loss function. And this is the regularization they have taken. Okay, and they are asking that which one is what kind of regularization is this in figure A, and what type of regularization is present in figure B. Okay, so basically the this kind of a curve, the circular one, as I mentioned, it's a L2 norm ball. The L2 norm ball is basically this. You can write it as x I over the dimension 1 to d whole square. Okay. So B is L2 regularization. This L1 is also a norm ball. So those who are familiar with the norm balls, they would already classify this as a L1 norm ball. Okay. So L1 norm ball is defined it as summation over I1 to D of x of I. That is the absolute value of each of the dimension of the vector. That is equivalent to norm ball. Basically, that is equivalent to definition of L1 norm. So the answer is that A represent L1 regularization and B represent L2. Okay, that was the question 3. Question 4. We are training a neural network to distinguish cat images. To increase the effectiveness of the learning, we blur, rotate, change some pixels. Okay, that is our data augmentation. They are doing it. Okay, which regularization technique are we using for the task? It's the data augmentation. That is the answer. The fourth one is data augmentation. Whenever you are corrupting a data, that is data augmentation. They just go to the weekly PPTs, watch the lecture. All the assignment questions are very straightforward actually. If you have understood what they have asked, it's easy. Okay. Question fifth. We are adding a Gaussian noise to the input before feeding to the feed for a neural network. Which regularization technique are we using it? So we are adding a noise. So addition of noise during training. So that's the answer. L2 regularization is also the answer because adding noise is equivalent to L2 regularization. Okay. So the option is the correct answer is L2 regularization. Okay. And adding noise. The two options are the correct answer. Option question 6. We are training a neural network with the following patient's parameter 2. When will the training stop? Okay, so patient's parameter, the number of ahead you were watching in the early stopping. Okay, so they have given the epochs, training error and validation error. Okay, so in the first epoch, this is our epoch. This is our training error. This is our validation. Training error was 4. This was 5. 3, 4, 5. 2, 3, 4, 5, 6. Then 3.5, 3, 2.2, 2, 1. 3.4, 3.6, 3.6, 3.3, 3.8. So you can see that the training error is continuously decreasing and validation it decreased up to this point and then it started increasing. Okay. So the pair ideally we should have stopped at ideally this seeing this data, the sweet point is epoch 3. The weight we have at epoch 3. But the patience is that we be just looking ahead, we be going for further thing. Okay. That 3.4 is there. So whatever was the normal sweet spot plus 2. That is 5 is the answer. That's what the patient's parameter. Okay, so the answer is 5 because we be taking it as 5. After that, we don't know it's not increasing, means it's not decreasing at all. It's increasing. Okay, so the answer is 5. Patience parameter, I haven't covered it, but you can just go through the lecture. It's easy. The patience, the sweet spot with the patience level, that's the number of parameters you can go ahead in the future, basically. We train different models of data and then use the bagging technique. We observe that a test error reduces drastically after using bagging. Choose the correct options. Different classifiers were selected as model. Errors of all models were correlated. Errors of all models are uncorrelated. So so basically, if you remember, we theoretical that it is something of k minus 1 time divided by kc. B was the variance of each model. C was the variance of correlated thing. Okay. So basically, we want is that this is the whole loss. We want it to be reduced basically. Okay, after bagging it. So this C was 0. That each and every model was uncorrelated, independent of each other. Then we are reducing by the factor of k. So the answer is error of all models were uncorrelated, that is independent. Okay. Given a feed for a neural network, below how many thin neural networks can be formed from it? Thin in the sense how many dropouts you can do. Okay. So the model they have given is something like this. This is the input. Okay. This is our input. This is output. And total number of 6 neurons we are having in between that. Okay. So we can either take on we can either take in the thin networks, either take a neuron or drop it. Two possibilities, and total 6 is there. So basically the thing is 2 to the power 6. So the correct answer will be 64. So why is 2 to the power 6? Each neuron can be present or absent. Only two options are there, and total 6 neurons are there. So 2 to the power 6. It's a combinations basically. Okay. So thin network basically the dropout they asked. Ninth question. We trained a network using a dropout technique. We observed that the weights earned by the two different neurons, H1 and H2, are the same. But while calculating the output, the contribution was H1 was greater than H2. Choose the correct options. H1 got dropped more than H2. Okay, H2 got dropped more than H1. The more the contribution is, the more number of time it was picked. Okay, I hope this is good because if both the weights are same and I need the number of contributions, how many time that particular neuron was present during the whole training. Okay, so that is a contribution factor. So if the contribution of H1 is higher than H2, that implies that H1 was present more number of time. So the answer is H2 got dropped more than number H1. So that's the answer. Now coming back to question 10th. We have trained 4 models in the same data set with different hyperparameters. The training and a validation loss of each model is given. So 4 models have been given. Model, this is training error, and this is validation error. Okay. Model 1, 2, 3, 4. The training error is 0.3, 0.9, 0.5, 1.9. Validation is 1.7, 1.1, 0.7, 2.3. Okay. We See, first model is there, the training is less, but the validation is higher. That is a more variance. The second one is there, both of them is approximately the same. The third one is there, it's also approximately the same, but the training and the testing both are further down than the model 2. In the last, both of them, the bias and variance is higher. So I will pick the third model. That is the training is 0.5 and validation is 0.7. Okay. So the model 3 has both low training loss and low validation loss. So that's the 10th question we have covered from the last year assignment. So I hope you enjoyed the today's session. So again, let's meet next week. And till then, goodbye.